Problem statement from Gate Physics 2020 reads as follows. In the center of mass frame, two protons, each having 7000 gigaelectron volts, collide to produce protons and antiprotons. The maximum number of antiprotons produced is. Assume the proton mass to be 1 GeV per c square, where c is the speed of light. And this is a numerical answer type question. We'll find the answer and fill in the blank over here. For relativistic kinematics problem, it's a good practice to just go through these p checks first. So we should know that all the frames we're talking about here are inertial or not. So here it's talking about center of mass frame. So center of mass frame we are talking about, and we have two protons which are colliding, and they have the same energy and they're moving in the opposite direction. So that's a given, because otherwise they if they're moving the same direction they cannot collide, they'll chase each other at a constant distance. So this means center of mass would be at rest, so this means center of mass would be inertial, right? Second is moving frame. There is only one frame, center of mass frame, so this question does not arise. This is not applicable. Number of dimensions, we will assume a simple one dimensional motion, and we will take this direction as the positive x-axis. Now it's first we need to look at the protons and some elementary particles. So on your screens you can see that the 6 quarks which make up the hadrons, and these are the symbols and the corresponding antiparticle symbols. So for instance, up quark will be a charge plus 2 by 3, and up anti-quark will have a minus 2 by 3 charge, and similarly baryon number for plus 1 by 3 will become minus 1 by 3. And a proton is made up of 2 up quarks and 1 down quark, so the total charge would be up down, so plus 2 by 3 plus 2 by 3 and 1 down, so that would be minus 1 by 3. So 4 by 3 minus 1 by 3 is 1, hence the charge is 1. Similarly, you can calculate the baryon number up and down, 1 by 3 plus 1 by 3 plus 1 by 3, that will come out to be 1. L is the lepton number, which we'll see in the last slide. So strangeness is 0 because up and down quarks are not strange. Correspondingly, antiproton is made up of, as I told you, of the antiparticle. So it will be U will become U bar and D will become D bar. So antiproton is U bar and D bar. So again the charges you can see is minus 2 by 3, U bar is minus 2 by 3, and again minus 2 by 3, and then plus 1 by 3. So minus 2 by 3 plus minus 2 by 3 plus 1 by 3 will come out to be minus 1. And similarly you can evaluate the B, and the strangeness will again be 0, and lepton numbers, as I told you, we'll see in this slide. So the first 6 entities that you see are what are called leptons. So for instance, these are electron, neutrino. For them the lepton number Le is 1, and muon and muon neutrino, again the lepton number L mu is 1 and Le is 0. Similarly for tau and tau neutrino, the lepton number L tau is 1, while all other lepton numbers are 0 even for this. Pion and kaons are your mesons, so naturally the lepton numbers will be 0. All the 3 lepton numbers will be 0 for mesons, and they are not baryons, so the baryon number is also 0. You can see for these 3. The protons and neutrons, which are baryons, so the baryon number is naturally 1, and they're not leptons, so their lepton number, all the 3 lepton number are 0 for proton and neutron. And yeah, that's it. And you can see strangeness, kaons are strange particles. So this is the complete. So this is a complete, not complete, a partial summary of the elementary particles, and there are some conservation laws that need to be followed for any interaction to occur successfully. Strangeness number has to be conserved. This means on the left side, the products, the reactants, and the products, the sum of the strangeness on the reactant side must be equal to sum of strangeness on the product side. Similarly for baryon, the baryon number on the reactant side, it should be the algebraic sum of the all the species on the right hand side, their baryon number sum. Similarly goes for L tau, L mu, and Le. Just to summarize, all these 5 numbers must be independently conserved. The key thing, they must be independently conserved. This means strangeness has to be conserved, baryon number and each of the lepton numbers have to be conserved irrespective of the other number. So this was the picture that was given to us. Before collision there were 2 protons which are coming towards each other at, let's say, at speed u. So these are their entities, these are their properties that we saw earlier. And so after collision we'll assume that p protons are produced and n antiprotons are produced. So the first law, rather the zeroth law, is the charge must remain conserved. So we'll write the charge on the reactant side. That will be 1 plus 1. This should be equal to, the charge is 1 times P plus minus 1 times N. So if I solve it, it will come out to be 2 equal to P minus N. This is my first expression. S must remain conserved. Strangeness is 0 plus 0. This is equal to 0 times P plus 0 times N. So this is 0 equal to 0. That is fine. B must remain conserved. So this is 1 plus 1. This should be equal to 1 times P. Note baryon number is 1 and minus 1 for antiprotons. This will again give us 2 equal to P minus N. The same expression as before. So 2 is also we have satisfied. 3. Li must remain conserved. This means Li means Le, L mu and L tau independently. So you can see the electron number is 0 on left side and 0 on right side. So 0 will become equal to 0. This, it will be of this form: 0 plus 0 equal to 0 times P plus 0 times N. This will be the scenario for Le, L mu and L tau. So 0 equal to 0. This is also satisfied. So from this conservation laws, we only gained one information, that P minus N must be equal to 2. These are two variables and we have only one expression. So we must seek some other refuge, and that refuge is of conservation of momentum. So what I'll try to do is I'll try to write the momentum for the reactant side first. So the momentum would be m times u, sorry, where m is the relativistic mass. So I can write as mu plus m minus u. Note that the speeds are the same. That's because it's given that their energies are the same, right? Of these two protons, it was 7000 GeV, and energy we know is gamma m naught c square. For both these protons, m naught is the same, so this would mean gamma must also be same. So gamma 1 must be equal to gamma 2. If that is the case, u1 must be equal to u2, their magnitudes, right? So they're in opposite direction, that I've assumed. Otherwise they'll not collide, they'll keep on, one will keep chasing the other. This should be equal to the momentum for these protons. So that would be, I'll write it like this. So this will be equal to, I am writing it as gamma pi m naught vpi, right? Gamma pi is the gamma corresponding to each of these protons that is being produced. M naught is their rest mass and vpi is the velocity. So I'm using this formula actually, gamma m naught times u, gamma m naught times u, plus again a sigma. This I will run from 1 to capital P, and again this J will run from 1 to capital N, gamma Nj m naught Vni, and this is, let's say, in negative direction. I assume this to be negative direction. You can assume in the positive direction, it won't matter, right? So LHS is coming out to be 0, right? This will get cancelled. So what we'll get here, and we take m naught common, and we'll also make it vanish. So this will come out to be sigma I equal to 1 to P gamma pi Vpi plus J equal to 1 to N gamma Nj. And this is a minus sign over here, that will come out Vnj. This is J, not I. Okay, so this is a complete expression, but this is a even more problematic because now we have introduced these velocities, and they are P plus N velocities. Gamma depends on velocity, so gamma is not a variable, but V are these velocities. So these are P plus N more variables. And this is only one expression. So we are stuck here. But let's go ahead and complete the analysis, and now we conserve the energy, and this is the formula for conservation of energy. And we are given that the energy on the left hand side was 7000 GeV. So this is 7000 plus 7000. This should be equal to the energy over here. So we wrote this formula, I equal to 1 to P gamma pi m naught c squared, right, plus J equal to 1 to N gamma Ni m naught c square. Rest mass is m naught for both. So what this will give us, 14,000 equal to GeV. By the way, the unit is GeV, and m naught unit is also GeV, right? So this will come out to, we will take m naught common, m naught c square common rather, this will come out to be sigma I equal to 1 to p gamma pi j equal to 1 to n gamma ni, right? So this is the expression that we are getting, and since we know that m naught c square is 1 GeV and this is also 14,000 GeV, so this term gets cancelled. So what will remain with is 14,000 equal to sigma I equal to 1 to p gamma pi plus sigma j equal to 1 to n gamma nj. This is nj, sorry, this is also j. Okay, so this is the expression that we are getting, correct? Now what we are required to do, we are required to maximize the value of n, right? So how can we maximize the value of n? That is the question, right? So that is the problem, how to maximize n or p. It's the problem, the nature will remain the same. So the way to do it is that, so now you have to see that so initially we had 14,000 giga electron volts of energy. Now that energy can either go in the rest mass, so that energy will go into two places. First is for the rest mass energy for each of these p and n protons and antiprotons, and then whatever energy is left, it will be gathered by the kinetic energy by some of these p plus n particles, whichever they are. So if you want to maximize more and more particles, it's better to assume that all the particles that are being produced are at rest. So that would mean is that this means all the energy, right, all the energy is going on into the rest energy, and on the right side there is no kinetic energy. If there is no kinetic energy, more and more rest energy particles can be produced, right? So that's the logic we are using here. So we are assuming that all the particles that are produced are at rest, so that maximum number of particles can be produced, because the left hand side energy is constant at 14,000. So we'll assume that. So if we assume all the particles on the right side to be at rest, okay, if we do that, then that would mean for a particle at rest, gamma equal to 1. For particle at rest, this would mean that gamma pi equal to gamma nj will be 1, because all the protons and antiprotons that are produced, we assume them to be at rest. So then this expression will become 14,000. So 1, you add 1 p times, this will become p, and then you again add 1 n times, so p plus n. Okay, so now we have got two expressions. So 14,000 equal to p plus n, and if you remember, 2 was equal to p minus n. This we got from the charge, if we balance the charges, right? So if we subtract the second expression from 1, you will get 13,998 equal to 2n, and n will come out to be 6,999. This is what was required, the maximum number of antiprotons, 6,999. I'll again reiterate that this was possible because we assumed that all the energy of the reactants is going to produce if we want to produce maximum number of antiprotons, then the best case scenario is that we'll assume all those products are at rest, so that maximum energy can go into the rest energy of the products. So the answer is 6,999. That's all. Thank you for listening.